Hello. So, today we're going to talk about um, confidence intervals for the mean when sigma is unknown. Intervals for the mean when sigma is unknown. And let's jump into it. This is very similar to section 6.1. So it's similar to 6.1, which we did in class on Wednesday. There are two new concepts that we need to be able to master. The first is the concept of a t-distribution, right? So we want to know how to interpret the t-distribution. This is a brand new distribution. We can look down here, in fact, so if we look at this graph, we can get an idea of the t-distribution. Now, the z-distribution, which is our standard normal distribution, is in blue, and that's the bell-shaped curve, right, with the mean equal to 0 and the standard deviation equal to 1. And we're familiar with the bell-shaped curve. We know that one, the standard normal. Now, a key difference is that a t-distribution, there isn't just one t-distribution. So a t-distribution, there's several t-distributions, and they're all based on the number of degrees of freedom. So degrees of freedom, the formula for degrees of freedom is, so you write df for degrees of freedom, is going to be n minus 1. And so the idea is that the larger n is, the more degrees of freedom you have, and the closer your t-distribution looks to a normal distribution. So I'm just going to try to kind of highlight here. Now, when n is smaller than 30, the t-distribution is really flat here, right? So it's really flat. It's not so much bell-shaped. But when we have n close to 30, now we're starting to get a shape that is closer to the standard normal distribution, right? So when we're doing our computations, what's important is the degrees of freedom. And again, the formula for degrees of freedom is going to always be degrees of freedom is n minus 1, where n is the sample size. And the second thing is, instead of looking at our critical values ZC, we're now going to have critical values that correspond to the t-distribution. So we'll have TC. This will be your critical values. So we'll get into that now. Okay. So here's the actual formula for how to arrive at the t-distribution when you're given a z-distribution. The thing to notice is in this formula here, we've got S, which is the standard deviation of the sample. Okay, so this t-distribution is not based on sigma, it's instead based on S. And it's a translation and a scaling of a normal distribution. Oh yeah, so I pointed this out before, but critical values of t are denoted by t sub c. Okay. The key thing, the hypotheses, what we'll be assuming when we're working these problems is that the population standard deviation is unknown. Okay, so that's the same thing as saying sigma is unknown. And we also will be assuming that the sample size is less than 30. Okay, because if the sample size is greater than 30, then we have
It's 9:30.
then the sampling distribution is normally approximated. Okay, so let's look at some more properties of the t-distribution. This is the first property here is the same as the normal or standard normal distribution. Mean, median, mode of the t-distribution are equal to 0. The second is that this is the same as a normal distribution and standard normal distribution. The t-distribution is bell-shaped and symmetric about the mean. Property number 3 is the same, which is that the total area under the curve is 1 or 100%. Now here we get to something that's different. So this is different. The tails in a t-distribution are thicker than those in the standard normal distribution. Okay, and another thing is that the standard deviation of a t-distribution varies with the sample size, but it's always greater than 1. Now remember, a normal distribution, the standard normal distribution, has sigma always equal to 1. Well, here with t-distribution, the standard deviation is going to change, and depending on the standard deviation, you get the thickness of the tails, right? And the key is that the standard deviation is always greater than or equal to 1. Okay, so in terms of let me just kind of explain this with a picture. In terms of the picture, right, if we have the standard normal, right, and you've got your mean at 0 and your inflection points at 1 and -1, what we're saying is that for a t-distribution, which I'm going to do in blue, for a t-distribution, the inflection point is always behind, right? So in order to still have your area under the curve equal to 1 and your inflection points further apart, further away from the mean, you're going to end up with a flatter curve, and you're going to end up with your tails. Let's see if we can highlight this. The tails, so see how the tail here, that tail is bigger than, or thicker, I think, than the tail for, right, the tail for the normal distribution. So the tail for the normal distribution is something like that, right, this little skinny piece, whereas the tail for the t-distribution is going to be thicker. Okay, so that's I think the way to remember a t-distribution is that it is similar to a z-distribution, except the tails are thicker and it's shorter. Okay, and the last property, which I was talking to you about before, is that the t-distribution actually is not just one distribution, but a whole family, a whole collection of distributions. And the shape of the distribution depends on the degrees of freedom. And here's a formula for the degrees of freedom right here. The larger n is, the closer your t-distribution approximates a normal distribution. Okay, and this is what we're saying here. After 30 degrees of freedom, right, the t-distribution is very close to the standard normal distribution. So this shows the degrees of freedom equal to 2. You can see this is the curve in black, and you can see that the tails are very thick, right, compared to the tail for the normal distribution. So here's the tail for the normal distribution. So it is very thin compared to the tail for the t-distribution when the degrees of freedom equals 2. But on the other hand, the tails, you can see that the tails are getting thinner as your degrees of freedom increase, right? And so when you've got a degree of freedom, sorry, greater than or equal to 30, now your tails are about the same thickness as the tail for standard normal. Okay. Now, so just like with section 6.1, we have critical values. Okay, and let me actually add a page above. And so with our critical values, here's the picture. The picture is you have a confidence level that you're given. So C is a confidence level. And C could be typical values for C. As we said in class, typical values are 80%, 90%, 95%, 98%, 99%. Now, corresponding to each of those, we've got, now imagine now we've got a t-distribution, so the tails are thicker. Okay, so this is my t-distribution. Let's take the example of 80%. So this area here, so the mean is still 0, because that's one of the properties of a t-distribution. And this has, I don't know how many degrees of freedom. Maybe the degrees of freedom equals, 5. I don't know. But this area right here is now, if I'm assuming my C equals 80%, this area is going to be equal to 0.8. And in order, okay, so this number right here is my critical value, my T critical value, or it's also called critical T. Critical T. Right? Now, how do I find critical T? It's very similar to how we found it before. So what I'm going to do is, now I'm just going to give the instructions for if you have a TI-84, because remember there will be no tables on the exam, no tables or charts on the exam. So make sure you look at the handout, check out the handout, the PDF that I posted, PDF posted on Moodle, that has instructions for how to find critical T. If you have a TI-89, a TI-83, and a TI-84. To check the PDF posted on Moodle to find instructions for finding critical values, critical T, with your calculator. Okay, so the instructions, I'm just going to give instructions for TI-84. So essentially, you will go to where you have inverse norm, and instead of looking for inverse norm, you look for inverse T. Okay, and so now you have inverse T, and the first variable here is going to be your degrees of freedom, and the second variable is going to be the cumulative area. So in this example, remember I said degrees of freedom equals 5. So I would need inverse T, and I would put 5 here for my degrees of freedom. And to find the cumulative area, remember the cumulative area is the area to the left. So I need to give them this area right here. And now what area is this? Well, this is where I use my picture. If all the area under the curve is equal to 1, then let me just do kind of a little sketch over here. So I've got this little piece right here. This area is equal to 0.8. And that means that these two areas have to add up to 0.2. Why? Because the total area, remember the total area needs to equal 1. So if the total area equals 1, and I've got this little middle piece that's equal to 0.8, that means these other two pieces have to add up to 0.2, because 1 minus 0.8 equals 0.2. So to find my cumulative area, which is this area right to the left, the area of the left tail, this area has to be half of 0.2. So this area must be equal to half of 0.2. So that's going to be equal to 0.1. So I put in 0.1. Now, what am I going to get out? I'm going to get out this t value here, right? And this is a negative t value. So in order to get the positive t value, I just multiply it by -1. So I would say my TC equals negative inverse T of 5 comma 0.1. And in general, the formula to find your critical value TC for a given C, here's what you do. You need to do inverse norm, sorry, not inverse norm, inverse T, and it's in the same menu as your inverse norm. And then you need to put in your degrees of freedom. And now in order to find that cumulative area, it's going to be 1 minus C divided by 2. Okay, and then you take that and you multiply it by negative 1. Right, because you want your critical value to be a positive number. Because the critical value is going to give us our formula for margin of error. So the formula for margin of error that we use, this is for when sigma is unknown, right? So sigma is unknown. This is what this entire section, that's mu, I wrote mu. I mean sigma is unknown. When sigma is unknown, this is the formula for the margin of error that we use. So you use your critical T, you use your sample standard deviation, and you still have this square root of n. So n is square root of your sample size. Okay. So, in words, this first step here, let me highlight this. You want to verify that sigma is not known. You want to verify that your sample is random and population is normally distributed, or n is greater than or equal to 30. Then you identify the sample statistics, n, x bar, and s. Okay. The degrees of freedom, the level of confidence, and the critical value. Now I'm going to say make sure that you practice finding it with your used technology, finding it with your calculator, because you're not going to be able to use tables on the exam. So you want to make sure you know how to find your critical T and your critical values, critical Z, on your graphing calculator. Then you've got your formula here for your margin of error. And you find your left and right endpoints by adding and subtracting the margin of error from the sample mean. So let's do this example here. So you randomly select 16 coffee shops and measure the temperature of the coffee sold at each. The sample mean temperature is 1.6 or 162 degrees Fahrenheit with a sample standard deviation of 10 degrees. Okay, so we're already getting some information here. Let's see here. So we can already tell what's going to be important, kind of. This is going to be important because you randomly, this is going to be important. The fact that it's random means you're going to have a random sample, so that's important. 16, that's important. That's going to give you your sample size. The sample mean temperature, so the sample mean temperature is 162. So already we've got that n is equal to 16. X bar is going to be 162 degrees Fahrenheit. Okay, with the sample standard deviation, this is going to be important, sample standard deviation of 10 degrees Fahrenheit. So that means S is equal to 10. Find the 95% confidence interval, bam. We've got C. C is going to be equal to 0.95. For the mean temperature, bam, they've told us. This is what we want. We want the mean temperature. So we're trying to get, sorry about that, our population, mean population standard deviation. So sigma is unknown, but we are finding a confidence interval for the mean. So this is what we want to pick. Confidence interval for the mean with sigma unknown. Now, population parameter being estimated is the mean coffee or mean temperature of coffee sold in coffee shops. Our point estimate is going to be X bar equals, what do we say X bar is? Let's see. X bar is equal to 162. Okay. And that's again from the question here. So we've got X bar equals 162. Our sample size, 16. So N equals 16. Margin of error. Ooh, what's our formula for margin of error? Well, formula for margin of error is E equals TC. E equals TC times S over square root of N. Now to find the TC, we need, and I don't have my calculator, to find TC, add a page after, add a page below. So let's put here to find TC. Okay, so I need to know that since N is equal to 16, my degrees of freedom are going to be N minus 1, which is 16 minus 1, which is 15. Right? Because to find my TC, I'm going to use negative inverse T, and I need my degrees of freedom, comma, that cumulative area. So it's going to be comma 1 minus C over 2. Okay. So I get minus inverse T. Degrees of freedom is 15. 1 minus C, so it's going to be 1 minus 0 point, isn't it 95? What's our, yes, 95 is our confidence interval, is our, confidence level. So we need 1 minus 0.95 over 2, and that's going to be minus inverse T of 15, comma, 0.025. And now we put it into the calculator, and what do we get? 2.131. So you should get 2.131. Okay, so here for TC, I'm going to put in 2.131. Okay, and then I need my S. What is my S? What's my sample standard deviation? Square root of, and what is N? N is equal to 16. So this is 2.131 times 10 over square root of 16. And that is going to be about 5 point something. What do we get? About 5.3. Okay. Say 5.3 is our margin of error. Now, for the distribution that is used, what distribution did we use? We used a T distribution. Why? Because sigma is unknown, only given S. Okay. All right. So we're looking good. Confidence level. We said our confidence level is 95%. So we say C equals 0.95. And, well, the units for the confidence interval is going to, remember, we're measuring the temperature. And we either did it in degrees Celsius or degrees Fahrenheit. Degrees Fahrenheit. So our units are going to be degrees Fahrenheit. And now when you do the confidence interval, you're going to go to stat, and then tests, and then you're going to go to T interval, and then you're going to input S equals 10, X bar equals 162, and I think you need to put in degrees of freedom. Degrees of freedom equals 15, and I think it spits out the answer, which should be 156.7 to 167.3. So here we put, so our final answer is going to be 156.7, comma 1, I forgot, sorry, 167.3. 167.3. Okay. So you also can write this as 162 plus or minus, what was our 5.3? Okay, you can also write it like this. Both of these are correct. This is correct, and this is correct. Okay, interpret the confidence interval. So we say with 95% confidence, we can say that the mean or the average temperature of coffee sold at coffee shops is between 156.7 degrees Fahrenheit and 167.3 degrees Fahrenheit. Okay, and so don't forget the units. We didn't. Our units are degrees Fahrenheit. And now notice down here where it says, or is it not possible to construct a it is not possible to construct a confidence interval, because if we were in a situation where we didn't know that our, here we go, let's go back here, where we didn't know that our temperatures are approximately normally distributed, that'd be the perfect time to say, hey, we can't form a confidence interval. Because in order to form a confidence interval, we are relying on the central limit theorem, which requires our temperatures to be normally distributed or our sample size to be greater than or equal to 30. Okay, so we're done with that problem. Now this is a little rubric here to tell you, are you going to use a normal distribution or a t-distribution? And it essentially depends on if sigma is known. If sigma is known, then you use standard normal distribution. Okay, and then here's your formula for the margin of error. If sigma is not known, then you need to use the t-distribution. Okay, and you'll use this as your formula for the margin of error. In both of these cases, again, it's worth repeating that in both of these cases, we are assuming you need to have either the population is normally distributed or n is greater than or equal to 30, right? So you need the population is normally distributed or n is greater than or equal to 30 for both scenarios. Now we've got this last question here we want to look at. The question is, do we use a normal or a t-distribution? So you randomly select 25 newly constructed houses. I've got information. Let's go ahead and knock it out. Randomly select. So that means my sample is random. Random sample. And I need that, right? Okay, you randomly select 25 newly constructed houses. Bam. That's my sample size. N equals 25. So I'm writing down all the information that I have. The sample mean construction cost. Watch this. Sample mean, which means average, cost is 181,000. So that means X bar is equal to 181,123. And the population standard deviation is 28,000. This means sigma is 28,000. Now, if they tell me that it's assuming, here we go, assuming construction costs are normally distributed, now I know what I need to do, because if either population is normally distributed, that's what we have, normally distributed, okay, and my sigma is known, so I need to use the standard normal. So my solution is to use the standard normal distribution. Okay, okay. All right, that's the end. Thank you very much.